Hi everyone. I'm a second-year engineering student, PhD, in electrical engineering, and today I'll be presenting some work that was part of a short-term project that was aimed at looking into the brain's response to music and also social interaction using optical neuroimaging methods. And this work is related to my main PhD work, which aims to identify a clinical biomarker for early-stage dementia using the same neuroimaging method. Dementia is a global health crisis, and it's one of the leading causes of death both in the UK and worldwide. And this is partly due to a lack of available treatments, but also a lack of non-pharmacological strategies to both manage or mitigate early-stage dementia. So one promising avenue for management is music therapy, and music therapy and listening to music in general has been linked to neuroplasticity, which just refers to the way in which the brain can change its structure, its function, in response to a prolonged stimulus. So for example, neurodegeneration. And so understanding this link is crucial to then be able to understand why music therapy may work to manage dementia. But the use of music therapy in dementia has not been investigated thoroughly, and a lot of this is due to the fact that current imaging tools, such as functional MRI, are difficult to use with vulnerable patient populations. They're very sensitive to movement, and you can't do paired experiments with them, which, as I'll explain in this study, we did do. So this is the alternative imaging method that we use. It's called high-density diffuse optical tomography, or HDDOT, and it allows us to investigate functional changes in brain activation. And this method relies on near-infrared spectroscopy, or NIRS, which works by taking advantage of this optical window where the skin and bone are relatively transparent to this light, but oxygenated and deoxygenated hemoglobin are the primary absorbers. And so we can shine near-infrared light into the brain and then measure the degree of light absorption, and that allows us to quantify relative concentration changes of oxy and deoxyhemoglobin. So that's what HBO and HBr are, respectively. And because active brain regions require oxygenated blood to function, we can look at changes in oxygenated hemoglobin as being directly related to brain activity. And so we can also get far more detailed information using HDDOT. So you take many variable length overlapping NIRS channels, which are defined by a light source and a photodetector, and you can use that to build up a very high density channel array covering the brain. And so in combination with anatomical information, we can produce really high resolution reconstructions of brain activity comparable to other imaging methods. But then this technique is also portable, it's non-invasive, and it has a really low sensitivity to movement, which made it ideal for this study. And so our main motivation with this study was the fact that currently there are no large-scale HDDOT datasets available, and we want to eventually be able to train larger models on this type of data, so we had to first collect our own. But we also wanted to test the robustness of the NIRS response to both external noise as well as to motion, and then also look at the impact of social listening on brain activity to perhaps provide an insight into why music therapy is so effective. And then, of course, it was also a really good opportunity for us to engage with the public about our work in dementia. So this was what the HDDOT device that we use looks like. It's called the LUMO, and that's what the cap is. And we have tiles, which are the black hexagons with the triangles on them, the green ones. And so we have tiles covering the auditory cortices and some of the surrounding regions on both sides of the head. And then in terms of the actual experiment, we had two separate tasks. So in the first task, we have two participants seated opposite each other. They're listening to two different sets of music, and there's a screen in between them so they can't see each other. And then in the second task, we remove that screen, so now they can see each other, they can move along with each other as they're both listening to the same set of music. Basically, the reason we designed this experiment in this way was to provide us with multiple classification problems or conditions. So in the first task, participants are listening to music independently. We had them listen to alternating blocks of a positive music task, which sounds like this. Maybe not. Maybe not, but just imagine like a happy music track. And then that followed by a negative music track, so sad music, and this was all film music. So the reason why you use film music is it's intended to produce a similar response in most people, but they're not going to necessarily know the music, by name. So we had multiple examples of both of these types of music so that we could investigate the degree to which different music types are encoded in the NIRS response. And then in the second task, we were focused on classifying between the solo and dual conditions. So here we're looking at the degree to which social interaction impacts the auditory response by comparing their responses from this task to the ones from the previous task where they were listening alone. And so this is what the data collection process looked like. It took place at a science and music festival, and in total we managed to collect 160 individuals, so 80 paired data sets. And essentially our first step after we collected this large data set was to be able to assess the quality of the data from each participant, and we were particularly looking at motion burden. And what we ended up seeing was that nearly 63% of the data sets collected were suitable for further analysis, and then of these data sets, the vast majority of them were of an equivalent signal quality to those collected in controlled lab environments, where we're explicitly telling participants not to move, which we didn't do in this study. And then from there, we can actually reconstruct the activation across all channels per participant. So we get these spatial activation maps of brain activity for each of the conditions. So these figures are reconstructions of brain activity averaged over 93 of our participants. And so for just the solo condition, we saw that there's more activation when listening to the positive, happier music compared to the negative music. And the activation was pretty localized, as you can see from the reddish-looking regions. And then when we compare that to the duo condition, we surprisingly saw lower magnitudes of activation, which wasn't necessarily what we expected. But we also recognized that these activation patterns occurred in a more diffuse way and in different regions of the brain. And so one reason for this might be related to attention. So people are more focused on the music when they're listening alone, but when you're listening with someone else present, they may be shifting their attention to that other person, paying less direct attention to the music itself. And so we also looked at statistical representations of this activation. And so these are T-maps, which show regions of significant activation in one condition relative to another. And so these figures are slightly difficult to interpret, but I think the main insight from them is that the primary region where we see greater significant activation in the dual conditions compared to the solo conditions, that occurs in the control network of the brain, which in part is related to how we divert our attention between different stimuli and choose what we want to process at a given moment. And so that's obviously interesting from the perspective of looking at social interaction. And then finally, we looked at network connectivity to examine how different functional networks of the brain were interacting during the task. And so these connectivity matrices are just plots of Pearson's correlation coefficients between any two brain regions. So you can see that in each of the four conditions along the diagonals, you see really strong within-network connectivity, which is what we would expect. But you can see in the off-diagonal regions, we also see some instances of very strong network connectivity. And more importantly, we see that across the four conditions, you can see different patterns of network connectivity. So your brain is recruiting different regions when processing the stimuli in each of these conditions. And so Importantly, we also observed that the highest number of significant correlations occurred in the solo negative condition. So 25% of all of the network pairs were strongly correlated, which is really high for a task like this. And so that's where we're currently at with this analysis, but now we have this large data set available to us, and we've assessed it in its entirety in terms of quality. So our next steps, I'm particularly interested in building classification models on this data to see the degree to which you can differentiate these different conditions, and then also looking at neural decoding models. So if it's possible to reconstruct the acoustic information from the NIRS responses themselves. And then finally, my main research focuses on interpretable machine learning for NIRS and dementia, and so seeing if we can use a data set like this to train those models before I actually have the dementia data ready. And then we also have these data sets paired, so people did them in pairs, and so it would be interesting to look at brain synchrony, which is basically just looking at the correlation between two people's brains while they're interacting or performing the same task, which is what is known as hyperscanning, and that would also help us look further into the physiological basis of music therapy and why it's been shown to be effective. And so, yeah, with that, I just want to thank my supervisor, Gemma Bale, and then also another PhD student in my lab, Amelia, who were really fundamental in designing the study. And yeah, that's our lab at the festival. So thank you.